Question states that there exists a particular oxide of iron with a somewhat complicated cubic unit cell. Your starting assumption is that you do not know the formula of this oxide. We know the density is 5.2 grams per centimeter cubed. At high temperatures, the iron oxide reacts with carbon monoxide to yield iron metal and carbon dioxide. When 2.660 grams of this oxide is allowed to react with excess carbon monoxide, the carbon dioxide product has a volume of 1.136 liters at 290 Kelvin and a pressure of 751 millimeters of mercury. 3 questions. What is the mass of iron in grams formed by the reaction? What is the formula of this oxide? And how many iron and how many oxygen atoms are present in the unit cell? So to begin, we need to find out what the mass of iron in grams is formed by the reaction. So we know the volume of carbon dioxide that is formed. So working backwards from that, we can find out the mass of oxygen that is present in that volume. So using the universal gas law here, ideal gas law, which is PV equals nRT, we can rearrange that volume over moles equals the constant times temperature over pressure. And this will give us units of liters per mole, right, which is molarity. So plugging in the values here, we've got the gas constant times the 298 Kelvin, which is given to us in the problem. And then I converted here the 750 millimeters of mercury into atmospheres, leave that here. The result is that we have a 24.759 liters per 1 mole at this temperature and pressure of the atmosphere. So using the liters that were given in the question, we can find out how many moles of CO2 were produced from the reaction. So we just simply multiply the liters times this ratio that we got, 1 mole per 24.759 liters, yielding a result of 0.04588 moles of CO2. Now, if you were to extract all of those lone oxygen atoms out of that, you would have the same number mole of oxygen, right? Same number of particles, size doesn't matter. So we have this amount of many moles of oxygen. Now, we want to know the mass of iron. So we do know the grammage, the mass of the whole substance. So if we take the moles of oxygen, multiply it by the atomic mass number there, which for oxygen is 15.999 grams per mole, we come out with a mass of 0.73407 grams of oxygen. Now, the total mass provided for us is 2.660 grams, subtract off the oxygen, leaving us with 1.9259 grams of iron. Now, taking significant figures into account, 3 digits is the most we can have here, so rounding the 3 digits, 1.93 grams of iron. So that is answer A. Now, question B is asking, what's the formula of this oxide? So, using the information that we have, we can find out the proportions of iron to oxygen. So we have the mass of iron. We can use iron's atomic mass, which is right here, 55.84 grams per mole. Now, times these across, the grams will cancel. So we know we have 0.03449 moles of iron that were produced with this reaction. So making this a ratio here, we want to know the ratio of oxygen to iron, or iron to oxygen. So we set this over each other, equal each other. When you divide this by this, you get 0.75. Now, what else yields 0.75 through division? That would be 3 over 4. So this proportionally is equal here. There is 3 oxygen atoms for every 4, sorry. Wait, hold on. I did something backwards. This is iron. Oops. Okay, my apologies. Using this value we got here, there's this many moles of iron per this many moles of oxygen, the ratio 3 to 4. Okay, so the formula, the bigger formula here is Fe3O4. Perfect. So that is the answer to question B. Now for 3, it gives us the information that the cell length has an edge of 839 picometers. Wants to know how many iron and oxygen atoms are present in the unit cell. So if we move over here, I've got the equation for density, right? Density equals mass divided by volume, rearrange mass equals density times volume. Because we can find the mass, the amount of grams within the unit cell, and we know we can find out the amount of mass in a molecule, we can find the proportion there as well. So rearranging, we plug in the density given to us, 5.2 grams per centimeters cubed, times 839. I converted this to centimeters, 10 10 to the minus 10 centimeters for the picometers, because picometers 10 to the minus 12. Cube that, so in the parentheses here, because cubing that will give us the volume, right? Side length cubed, volume of cube. So the density times the volume yields us the mass of 3.07107 times 10 to the minus 21 grams. So now we need to find out the amount of mass within just one of those molecules. So we take the atomic mass for iron, multiply it times the 3 atoms per mole, and then we have the 1 mole Avogadro's number here. That'll give us the amount per just the amount of mass per just the 1 atom times by 3 atoms. Sorry. So calculating that out, we get 2.7818 times 10 to the minus 22 grams for 3 atoms of iron. Now doing the same here, we've got the atomic mass value divided by Avogadro's number yields the mass of just 1 atom of oxygen multiplied by the 4 atoms that we have, yielding this value 1.06270 times 10 to the minus 22 grams. Now adding these together, we have 3.8445 times 10 to the minus 22 grams. So that is the mass of one of those molecules there, this oxide. So if we know the total amount of mass in a unit cell, and we know the mass of the molecule, we can find out the ratio there if we take this number over this number. So we do that here, divide it comes out to just shy of 8. So we can easily assume, due to calculation, rounding errors, whatever, this is 8. So if we have 8 of those within the unit cell, we can just simply times across the empirical formula, giving us 8 times 3, 24 iron atoms in the unit cell, and 8 times 4, 32 oxygen atoms within the unit cell. So for question A, 1.93 grams of iron. Question B, Fe3O4, and for question C, 24 iron atoms, 32 oxygen atoms in the unit cell.